Welcome back. Let me share my screen. I'm still in the second part of session 6. We are talking about data preparation, data pre-processing, and we spoke of data cleaning. We had talked about binning as one approach to basically smooth out and basically eliminate the noise. Another approach that we would wanted to use was regression. Regression is a very important topic, and it has many application. And I just want to briefly explain to you what regression is in this class. Once again, keep in mind that in this class we are always interested to introduce some terminologies. You are going to have a course specifically on noise, on data preparation and data pre-processing, a complete course on data preparation. So we are trying to familiarize you with with this process. And when you get to the next stage of an advanced course, you should be armed with the proper terminology and basic understanding of what the data preparation is supposed to be. Now, I collected the data, and the data seems to be show to some sort of a trend. It seems that when X is actually increasing, Y is also increasing, and the data is actually moving this way. I can see the trend. I'm a human. Remember the big difference between what we are discussing as a human intelligence versus the computer intelligence. At the moment, computer has no brain. Computer has processing power, but the brain of the computer is you. You are going to be coding the program. You're going to programming and coding and giving the instructions to the computer as to what to do. So keep that in mind. There is a big difference between human intelligence and what you want a computer to do for you at the end of the day. Now, since there is a trend, you could potentially argue that I could potentially have a kind of an estimate of what this trend looks like. And one of the easiest estimates would be considered a linear regression line. So there is a line here. This is the line. Now, I'm going to show you a few links in a moment. You have the data points, and the data points on a vertical basis have a distance between this point and this point. This is positive error. This one is under the curve, under the line, and this is going to be negative error. Error is there, but it's negative. You don't want that error to have an impact. You don't want plus and minus to cancel each other out. And the way you're going to think about it, you're going to take these differences and you're going to take them to the power of 2. So you have the error here and you have the error here. When you take them to the power of 2, they become positive. You're going to actually add all of these errors together, the one on top of the line and the one at the bottom of the line. You're going to add all of these errors together. Your intention is that you want to have a line where the error is going to be minimized. Let me give you a little bit of a feeling what I mean. If this line is actually a little down, what happens on the error on top, they become larger and larger and larger. And when you take it to the power of 2, it becomes extensively larger. Of course, the error at the bottom seems to be smaller. They seem to be insignificant, but the error on top became quite significant. Now imagine that the line is actually going a little bit higher. So what happens? The error on top could be smaller, but the error at the bottom, although negative, to the power of 2 become positive, it's going to become bigger and bigger and bigger. So therefore, that's not the suitable approach. That's not the suitable line you want to do. So what's the purpose? What's the idea? You want to have this line in a place that it's almost passing through the data and it's going to be balanced on the positive error and the negative error. Let me share my screen with you. And once again, this is the error function. This is a line, and this is considered regression line. And these are the observed values. These are actually the observed values, but this is the line I'm assuming that I'm going to replace the observed values with. It's supposed to be mx plus c. M is the slope of the line, c is the constant, in this case b. So this is the error we spoke of. Now, if you take a look at this, all of these little points on the 2D map are going to give me errors, some of them positive, some of them are going to be negative. And I would like that error to become minimum. And then what happens is that I'm going to take that differences, I'm going to take that differences and I'm going to take them to the power of 2 and I'm going to sum them up, and I want to have this minimized. I want to design the slope of the line and the constant in a way that when I put it in, the error is actually minimized. It's a line. But before I actually insist on the line, keep in mind that it doesn't have to be a line as in linear line. It could be just a curve that could potentially go through the data, and this could be a second degree. This could be a little bit non-linear, I would say. So this is a kind of a non-linear polynomial regression. So I need you to be aware of that. But linear is the easiest one for us to discuss, so that's what we are going to do. Let's take a look at my slide again and take a look at this equation. Someone has done that optimization. We don't want to go and discuss that in detail in this class. This is not necessarily a math class. We do have math component, but we are not here to prove an equation. But I want to explain and just to give you what the slope is and what the constant is and how the line is going to be forming. So the slope is going to be calculated in the following way. You need to find the x hat. X hat, what does it mean? X hat is the average. You're going to put all of these points and shadow them on the x-axis. You're going to have a bunch of points here. All of them is the shadow of the observed data points. You're going to take the average. How do you do that? You take the x's and x's and x's and x's, you sum them up, you divide it by the number of samples. So let's call that number of samples a small n. So if you add up all of the x's and you divide by the number of samples, you will get the average. Take a look at y hat. Y hat, all of these data points are going to be mapped onto the y-axis. You're going to have a lot of points here. You're going to add up all of the y's, and then you're going to divide it by the same number of n. Keep in mind, the n is the same. The number of points, whether you look at them on the x-axis or you look at them at the y-axis, the number of points is going to be exactly the same. So let's call it n. So what do I have? I'm going to have the data points mapped onto the y-axis. I'm going to add them up and I'm going to divide it by n, and I'm going to get my y hat. So far, so good. The next thing you need to do is that every data points, every x, you're going to subtract the average from it. So the average is going to be taken out of all the x points, of all the y points, and you're going to multiply them per point. So if I take a look at this point, it has an xi, it has a yi. So this is x1 and this is y1. I'm going to subtract x1 by the x average. I'm going to subtract y1 by the y average. I'm going to actually multiply that per point. And I have n point. And then what I'm going to do, I'm going to sum them up, all of these little calculations, pairwise calculation, and it's going to give me the summation that I need. That's going to be the numerator. Now the denominator is going to be only applied on the x-axis. So you already have the x hat. Remember, x hat is a summation of xi divided by n. And then you're going to get the xi minus x hat or x average. And then you're going to take them to the power of 2. And then you're going to actually sum them up, the total one. That's the denominator. You do this division and it's going to give you the slope. So the slope of the line is going to be calculated the way you see on the screen. Now, take a look at the C, the constant. We see C because C is the first letter of constant. It's going to be the y average minus mx average. This is the number now, this is a number now, this is a number you just calculated on top, and that's going to give me my constant. Now, if you take a look at this, there are different ways of calculating the m and c. And as you can imagine, some people have actually replaced the average by summation of xi divided by little n. the summation of yi divided by little n. People have done this. This formula is a valid formula, but at the same time, people actually have gone and reformatted everything. And if you do that little n, you're going to actually find a different approach. So instead of subtracting the mean, you could potentially let it go because you brought the n into the picture. Remember, this n is supposed to be underneath of the summation of xi, on the summation of yi. When you do that and you rearrange everything, this equation is the same. So don't consider this to be any different from what I have shown you. This equation is the same. So it's easier to see it here. The summation of y divided by n, what was that? Y hat. The summation of x divided by n, what was that? X hat. And you have the m as in a slope that has been calculated. So these are exactly the same. So if you take a look at this Math is Fun website, you could potentially have X number of sunshine and Y number of ice cream sold. If you follow this equation instead of the other one we spoke of, all you have to do is to calculate the XY, sum up the X, sum up the Y, and you're on your way to calculate M and B. So what did we do here? In this approach, I'm going to do x to the power of 2, y to the power of 2, x to the power of 2, xy, and I'm going to actually sum them up. I'm going to have summation of x, summation of y, summation of x2, summation of xy, and I'm going to put the numbers here. Summation of xy, summation of x, and summation of y as two separate numbers. You're going to multiply them, summation of x to the power of 2 and summation of x to the power of 2, and that's going to be your slope. Similarly, you're going to go and approach and find the constant, the constant c, and then this is going to be your line. So if you had these in a 2D scenario, you find a line that is going to be almost resembling the trend, potentially as close as it gets to the data points. Keep in mind that we consider this linear. And you could potentially make it even more accurate if you have done polynomial or if you have done non-linear regression. Okay, so that's the that's what we had in mind. At the same time, when you calculate this, so if you have any data missing here in between, you can't go back to the observation. You don't have access to the observation at the moment. Everything is given to you via the client. And since you have a missing data, what you're going to do, you're going to go there and you're going to actually find that missing data using this line. If it is a linear regression, if it's going to be a nonlinear regression, now you have the equation. All you have to do is to put the x here and then come up with the y. And then that's it. You are going to fill in the gap, fill in the blank. One of the things that you need to know, though, is called correlation. And we are going to talk about correlation hopefully down the road. Let's take a look. The next one is basically outlier. And I'm going to explain this in the next recording.